Welcome all. In today's video, we will be talking about electrical and optical confinements in LEDs. So, first of all, we should understand that what exactly is electrical and optical confinement, what is the need of these electrical and optical confinements in LEDs or laser diodes, and how it is achieved. To understand electrical and optical confinements, you should understand the working of LED. So all of you know, I'm just giving you a recap. So how exactly an LED works. So for LED, you always need a direct bandgap material. So that was the first condition, bandgap material. So of course the material should have minima of conduction band and maxima of valence band lying for the same momentum vector k value. If this is the case, then it is suitable for LED application. Now in normal conditions, even this forward bias is equal to 0, you will have some barrier potential and you will have a junction region. Right? As you increase the forward bias, what will happen is that uh, more electrons that will diffuse in this region and holes, they will diffuse from the P region, and there will be high concentration of electrons as well as holes in the junction region. And because the material is direct band gap material, they will be combined and they will give you light. So this is how LED works. However, the second condition is that delta N or delta P that is being diffusing inside this junction region, that should be quite high, so that a large photon flux is generated and we get a net output light or light output. So here the word net. Okay, why I am saying that net output light? Because once the light has been generated because of some recombination, there is a high chance that this photon will be absorbed again, right? Because ultimately it is a semiconductor, and in semiconductor, if a light has been generated, there is very high chance that it will be absorbed and it will be create electron hole pair. So you will get nothing, and that's why it is very important for electrical confinement. So you can assume it like this, that some photons are actually being generated. Okay, let's assume 100 photons, they are being generated in some area that is quite large. What will happen is that all these electrons that will be generated, and again they will be absorbed by the same material, and that's why you will get nothing at the output. That's why it is very important that even if all these 100 photons, if they are being generated in a very thin region, then of course the probability that light emission you can get at the end, that will be quite large. Okay, so I have given you one example. So in this way, Okay, if all these lights are being generated only in some region, very thin region, then the light output is possible. To understand, you can assume that there is a large field over which the rain drops are coming, right? If you want to collect these water from these raindrops, these rain should be quite heavy, because as you are getting water droplets from the rain, and that is also being consumed by the earth or the ground, so no water will be available to collect on the ground. If you want that, you should have a sufficient water that should be flowing. Then either you increase the rate, okay, very heavy rain, or if all these rains are actually being uh, it is raining on in a very small region, all the water is pouring in very small region, then only you will get a sufficient water. So that is your electrical confinement, why it is important. Now optical confinement is related with the same concept, that if a light is being generated in this region, and if this light generally in LEDs, they are spontaneous, okay, or in any material, in which direction the light will go you can't predict, so almost like 360 degree. In fact, uh, the whole solid angle, anywhere in the sphere it can go. If it goes in the other side, then of course it will get absorbed, because there is a large region over here, and the efficiency that you will get out, okay, that will be very small. And that is why it is very important that all these lights should be confined only in a particular region, so that you get sufficient output. So ultimately, electrical and optical confinements are important to increase quantum efficiency. Okay, so of course, internal quantum efficiency and external quantum efficiency respectively. To increase the internal quantum efficiency, it is very important that all of these electron hole pairs, they are being generated in a very small region, so that each and every part of the material in that particular small region, they are only generating, they are not consuming photons. Okay, so that is that consumption probability is very low, and once the photon has been generated, we should guide them so that we get a net optical output, so eta external. So this is related with how to increase quantum efficiencies of LED or laser diodes. So I hope that I have answered these first two questions. What is electrical confinement? Electrical confinement means confine all these electrons and holes in a particular region. And optical confinement means all the generated light that should be only it should be going from the generation point to the output. It should not go on the other side of the material. Okay, so that is optical confinement. Why it is needed? Of course, to increase the quantum efficiency. Now, how it is achieved? As in case of LEDs, I have talked about, if you see the P side or N side, and if you plot the carrier concentrations as a function of X, you will find that carrier concentrations are quite high for electrons, and then it goes to particular level, and then it exponentially decreases in p side. Likewise, the whole concentration that is very high on the p side, and then suddenly in the junction region it goes low, and then decreases, right? So this value will be Pn0, and this would be Np naught. So that we all know from the diode equations. Now if you see in this junction region, with some little forward bias, a lot of electrons and holes are present. In this region, if we talk, okay, in N region, we have very high number of electrons, but finding holes that is actually quite low. In the P region, holes are quite large, but electrons are small. For recombination, of course, that happen from one electron to one hole, right? And that's why almost if they exist in equal number, then it will be maximum, right? Or the lowest concentration that will decide the rate of recombination. Okay, the highest concentration that will not decide. So in this region, in the junction region, light emissions are most probable, and of course it will be generated. Now, can we achieve even higher carrier concentrations? So that is actually your electrical confinement. To achieve that, what we do is that we don't use a very simple P and N type gallium arsenide. Let's assume it was gallium arsenide. We don't use P type gallium arsenide and N type gallium arsenide, only two layers. We use 3, 4 layers, and the objective is that when the P side, they will send you holes, N side will send electrons over here, and if this active region that is made up of gallium nitride over here in this example, so this has lower band gap. Okay, so the aluminum gallium nitride, the band gap may vary from 4 to 5 electron volts, so depending on the value of x. This is also 4 to 5 electron volts. Gallium nitride has approximately 3 electron volts or 3.5 electron volts. Okay, let me see what exactly it is. It is around 3.5 electron volts. And if you give a little forward bias, of course, the structure will become like this. The energy band will tilt. Okay, and all these electrons which was in the n-type gallium, aluminum gallium nitride, that will be collected in this region only. Lot of electrons. Likewise, holes in this region, they will follow the bubble model, and they will be collected only in this region. Okay, gallium nitride or the active region only, because there are a lot of carriers in a particular region, and that's why a lot of light will be generated from this active region. Okay, so that was electrical confinement. However, if this gallium nitride width, if it is quite large, then this will be having a continuous band type of structure, and the maximum electrons they will actually occupy the lowest energy levels. However, if you make it a quantum well means if this distance, thickness of the gallium nitride D is approximately, let's say, 5 nanometer, 5 to 10 nanometer, then in that case the energy levels over here that will no longer be uh, continuous, but that will be, you will find a very well defined energy states. Okay, like this. And the probability of occupancy of this first energy level, let's assume n1, this is n2, that will be quite large. If I plot it, so if I plot it, it will be quite large at this point, and then it will be smaller at this. Okay, so the density occupancy is quite high for n1, and that's why it is very probable that all these electrons they will occupy the n1 state. Likewise, in the valence band, you will not have continuous holes, but they will be at, let's say, n1 and n2, like this. So the transition corresponding to this Eg1 that varies from n1 to, let's assume, y1 and y2, corresponding to En1 minus Ey1, that is quite large, and you will get a spectra corresponding to Eg1. You plot it in terms of energy, that will be quite high as compared to Eg2. So generally it is almost like more than 100 times lower. Okay, 100 times lower. That is how, in case of, that's why we have in laser diodes, we need these quantum wells. In fact, we don't have only one quantum well, but a series of quantum wells. Okay, so a structure will be something like that: aluminium, gallium nitride, aluminium, gallium nitride, and then lot of quantum wells over here. So in between, you will be having gallium nitride, then algal, then gallium nitride, then again algal, then again gallium nitride, like this. So of multiple quantum wells, they are actually being created. For laser diodes, we also have special reflectors on both sides. Okay, so that is called the Bragg reflectors that we can fabricate on the top side as well as bottom side. Okay, so in this side we can fabricate Bragg reflectors. On the top side also we can have Bragg reflectors that has a reflection more than 99%, and here reflection can be more than 99.99%. Okay, so all these light that will go in one direction, something like this. Now coming to the point that how we achieve uh, this optical confinement. is that so this relation is given as uh, band gap energy Eg and refractive index N. They have a relation in semiconductors. Okay, this was given by T.S. Moss. In fact, this is a modified version. T.S. Moss first he had explained the relation between refractive index and band gap in semiconductors in around 1949 or something. Quite uh, old research. Everyone knows that if band gap is increasing, that means the refractive index has to be small. From this equation also you can see that if you increase band gap, that means refractive index has to be small to satisfy this equation. So all high band gap materials they have lower refractive index. Now if you know this concept, then now your answer for this will be entirely different. So how do we achieve optical confinement? Now you can get it very easily. So this region, that is aluminum gallium nitride. So of course as you increase x, we are moving to this line. So x is equal to 0 and x is equal to 1. When x is equal to 1, it becomes aluminum nitride. Sorry. So from this side, x is equal to 0 over here, x is equal to 1 over here. So you are moving around this line. Okay, and you have gallium nitride which has band gap of approximately, you can see, 3.5 electron volts, and this may be 4 to 5 electron volts depending on the value of x. If x is small, of course the band gap will be small. If x is large, band gap will be large. Higher band gap materials, they have lower refractive index. So let's assume it is N1. Of course ultimately this is the same material, so it will also be having refractive index N1. However, in this region, active region, gallium nitride, it will be having refractive index N2, where N2 is greater than N1, right? So you have N1, N1 and N2 in terms of refractive index, where N2 is greater than N1. So what will happen is that this structure will work as a waveguide, as in case of optical fibers, right? In case of optical fibers, what we have? We have core which has N core and then N cladding, right? Where N core is greater than N cladding, and that's why there is a high chance of total internal reflections. So any light which is trying to go outside this gallium nitride region, they will be transferred back because of the total internal reflection. So this is how we achieve the optical confinement. Now all the light, they will be more confined in this gallium nitride region, right? So electrical confinements, that's giving that high number of photons in this region will be generated, and optical confinement say that this light will not leave this gallium nitride region, and that's why this gallium nitride region is also called active layer or active region in terms of LEDs or laser diodes. So I hope that you have understood what is electrical confinement, what is optical confinement, and why it is needed and how to achieve that. Okay, to achieve it, you must have a material with high refractive index sandwiched between two layers which is having low refractive index, or you can say that higher band gap. So in this way you can achieve both electrical as well as optical confinement. So both are there, electrical and optical confinement, both are satisfied in this structure. Here I have shown you, so this image is being copied from somewhere. Sorry that I have not given the reference. Anyway, so if you see, there is one problem over here is that this light emission that will not be exactly circular, but it will be a little elliptical, okay, because of diffraction. Of course, diffraction that is proportional to the slit width, right? So 1 by slit width. Okay. So smaller slits, they will give you more diffraction, and that is why if one layer is actually, if you see the layers, it will be something like this. Okay. So this W and L, and this thickness T, right? They are not same because this thickness is actually quite small, so it will uh, expand more in this direction and less in this direction, okay, because L is quite large. So you will have an elliptical output. Okay, in this region it will not be much wider, but in this region it will be quite wider. Okay, so that is what exactly it wanted to show. That was the one problem for edge emitting diodes, and that's why people have come to this uh, surface emitting or vertical cavity big cells, or vertical cavity surface emitting lasers. Okay, big cells. And it was also very easy to integrate optical fibers from these laser diodes. These are especially used in optical communication. For lighting purpose, we generally use only LEDs. Okay, so LEDs are more than sufficient for lighting purpose. The only thing is that its luminescence parameter that should be. I think that I have covered this topic in quite details. If you, even if you have any questions related to the material or other things in this topic, you can ask me a question in chat box. I will answer it. Okay. Thank you.